Peter, I saw this scary PDE in my textbook. It says it models heat, but I don't see how a bunch of derivatives explain temperature.
That's the one-dimensional heat equation, Stewie. It models how heat diffuses along a thin rod over time. Here, U of x and t represent the temperature at position x and time t, and alpha is the thermal diffusivity constant of the material.
So partial U with respect to t is the rate of change of temperature with respect to time?
Exactly. And second partial U with respect to x tells us how curved the temperature distribution is in space. If the temperature at a point is lower than its neighbors, heat will flow in, increasing the temperature. And that's what causes diffusion.
And the equation says the time rate of change is proportional to that spatial curvature?
Yes, it's derived using Fourier's law of heat conduction and conservation of energy. For a small segment of the rod, the net heat flow in minus the heat flow out equals the rate of internal energy change, which leads you straight to this PD.
How do you solve it?
Typically using separation of variables, assuming boundary conditions, like fixed temperatures at both ends, and an initial temperature profile, U of x and 0. You turn the PDE into two ordinary differential equations and solve for eigenfunctions and Fourier series coefficients.
So, we break it down into simpler parts using orthogonal functions?
Precisely. And depending on the boundary conditions, Dirichlet, Neumann, or mixed, the solution evolves differently over time.
I get it now. It's like the math version of watching coffee cool down.
Exactly. If this made the heat equation less intimidating, follow for more math that brings the temperature down. And share it with someone who still thinks curly D is a fancy 6.